Okay, so today we are continuing with the solution of a particle in a harmonic potential, or as it's known, the harmonic oscillator problem. And as we have described in the beginning of the previous lecture, this is a very ubiquitous problem in physics for the simple reason that any potential that has a minimum could be, at least for low energies, be described as a harmonic potential. And I just wrote down what we did in the previous lecture. Basically, we wrote down the Hamiltonian. For no good reasons, we expressed it in the terms of these two operators, and we gave them names. Creation and annihilation operators sounds very cool, but at the moment it's not clear why they have these names. We wrote these two operators are not Hermitian operators, therefore they don't represent any physical observable, although they have a huge influence on the physics of the system, but they are not corresponding to any observable. And we can write a combination which is Hermitian, and actually we can express Hamiltonian in terms of this operator, which has a name, the number operator. Okay, so far we are just dabbling with definitions. The reason that we play this game is twofold. One, it makes solving this problem very easy, unbelievably easy. And the second, it has deep physical influence, meaning, which goes beyond this particular problem, and I'll discuss it a bit towards the end of today's lecture. Just because of the holiday, we are finishing at 3:30. Okay. So, one thing that is immediately clear here, it's almost trivial, but I'll write it down. H commutes with n. The Hamiltonian commutes with the number operator, meaning that if we know the eigenvectors of this guy, we will know the eigenvectors of the Hamiltonian. Why does it commute? Because an operator commutes with itself and commutes with a constant. Okay, so now our first goal is to find the eigenvectors and eigenvalues of n. Now I'll just express it in a formal language. If we operate on some eigenvector n, I didn't define yet what it is, we'll get some eigenvalue and the corresponding eigenvector. So that's our goal. And if it's indeed an eigenvector, of course it has to fulfill the orthogonality condition. Okay. Actually, it tells me that the eigenvalues of H Once I know what is the value of n, I know also what are the values of the eigenvalues of the Hamiltonian, meaning the energies. Now I don't know what is n. I can guess already at this point that it has to be quantized. It can't be a continuum just because this is a potential that goes to infinity, meaning that all states are confined in this case. So I have a discrete set of values of n, but I don't know yet what they are. Okay, but I do know something. Basically, p square is a square of the momentum, and x square is the square of the position. Definition. These squares are positive numbers, meaning that the value here must be larger than 0. Can't get here anything negative. Just looking at the potential, its minimum is at 0. I can't get a confined energy which is lower than 0. Okay, so these were very general considerations which will help us to get to the solution. Okay. So, what can I do with these operators? First of all, in general, it's always a good idea, if I don't know how to proceed, check the commutation relation of operators, because it might turn out to be useful. Okay, no problem. Let's write it down. Okay, I don't know how to do this definition, but if I substitute to this definition, I certainly know what to do. So this is equal okay, so I have here 4 pairs of commutation relations. So I have between x and x, it's 0. Between p and p, again 0. And here I have 2 commutation relations between x and p that are not 0. Okay, let's write them down. Just wrote down the 2 terms that survive here. X and p, we have already calculated this commutation relation. It's I h bar. Okay. I'm left here with 1. Okay, so I know that A times A digger minus A digger A is equal 1, and I will use it in a moment. So let's put this result and keep it in a moment we will use it. Okay. Actually, from here on, at least for the next half hour, I'm forgetting about X and P. All they were useful is to give me a commutation relation on A and A data. Okay. Just before leaving commutation relations, I can ask what is A digger, but that's easy to pull it out. And A and for the simple reasons, and any commutation relation of an operator with itself is always here. Okay, so that's trivial, but I just wrote it there. Okay. I want to see what is the result of the operator n times a. Okay, I'll use the definition of n. And I want to take A dagger A, which appears here, and write it down as 1 minus A dagger, but with a negative sign. Okay, all these are operators, of course. Okay, what did I get here? Basically, I got here A times A dagger A minus 1 Okay, I have to all the time be careful not to exchange them without to take into account the commutation. But if I have a lone standing A, it doesn't matter if I multiply it from here or from here. Here I took A dagger A as n, as here, and the first one I put before the parentheses. You're unhappy with something? Because, okay, let me put here another step. Okay. So now I can pull the A, this A and this A before the parentheses. Okay, I can do the same game. So I'm taking now A dagger and writing down A dagger 1 plus just again from the commutation relation. Okay, so except doing some exercise with the algebra of operators, what did I gain out of it? Actually, it tells me something very profound about the operator n. Why? Let me define a wave function, phi. Which is A operating on n. I claim that this vector is also an eigenvector of n. Let's see. So if it's an eigenvector, I should show you that operating on it with n will give me some constant times this vector. Let's see. Oh, but this guy, we know what it is. Okay, n that operates on n gives me n times vector. One that operates on n gives me n. Sorry, n. But these are numbers. And 8 times n is just phi. So I got n minus 1 times phi, meaning that this is also an eigenvector of n, but not just any eigenvector, an eigenvector that has an eigenvalue that is the same as the original n, just subtracting one from it, one lower. Okay, the only thing I'm left here, I'm not sure it's normalized. So I'll check normalization. Remember, I'm now operating to the left, so it's 8 degrees. This is not a Hermitian operator, so I have to be careful. But this guy just gives me n. So this is equal n. So now I can give this eigenvector a name. It's n minus 1, because that's the naming schemes that we have. An eigenvector that gives us an eigenvalue of n minus 1 is this guy. Sorry. In order to normalize it. Sorry. And so on and so forth. I can go down the ladder each time subtracting 1 and getting a whole. Once I know one of these eigenvectors, I can go down the ladder and find more and more of them. Should be careful about correcting the normalization, but that's that. Okay. Now, from a very simple consideration, I'll get a very surprising result. We mentioned a few minutes ago that this value, the value of the eigenvector, of the eigenvalue, can't be negative because of the energy. If I'm playing with this guy for any number, nothing stops me from going down to more and more negative. except in one case. If n is an integer, once I get to 0, I'll get here 0 built in, and I can't go any further down. Meaning, seems almost a trivial statement, but that solves the problem. Now I can, without anything further, without to tell you anything about what are the eigenfunctions, can tell you I know the spectrum of a harmonic oscillator. Equal distance energies starting with half h bar omega. Because the first one is 0, 1, 2, 3, 4, I can't get anything else. So that's what I said, that basically I solved the problem without doing anything. Didn't solve a differential equation. In a moment we'll say what is n. This will force me to solve one simple differential equation. Okay, I can write the ladder the other way up. See what's happening here. So, in principle, any eigenvector of this system, or let's say, let's start with a simple case of a dagger of n. Just by the definition of what it does, define again, let's play our usual game. A different phi claims that n of phi is also an eigenvector of n. We did the calculation. I'm just copying the definitions that we had for n a dagger, and I get here sorry, n plus 1 phi. I just have to correct the normalization now. And we get a dagger so let's assume I have the ground state. I want to build any state n So all I have to do is operate on the ground state n times, and I'll get the n eigenvector. The only thing I have to worry about is correcting normalization. Okay, so instead of finding all eigenvectors, once I have this guy, I have all of them. So let's find this guy. Okay, but before we do it, now we can understand the names that we gave to the operators. Number, so pulls out the n, the integer, so it's a number operator. Creation, I'm putting in a packet of energy h bar omega each time I operate with this operator. So this is an operator that adds h bar omega energy to the system each time that I use creation. If I think about this energy as a particle, let's say a photon, so it creates a photon each time with a value of energy h bar omega. In a few moments, I'll talk about what is the connection to photons, because this is not a photon, this is a particle in harmonic potential. But the idea is the same. The photon is putting in a packet of energy into your system. Here it's putting in a package of energy, a quantum of energy into the system. Annihilation, the same thing. I'm removing h bar omega of energy from the system. That's annihilation or destruction, if you prefer. So we understand the names. Now, what is this guy? Okay. To find out what is this guy, if I'll try to remove another package of energy off this, I'll get 0. So this is the differential equation that I have to solve. Why is it a differential equation? Because now I'm going back to use the definition of x plus some constant p. I'm just writing it down explicitly. I just replaced p by I dou h bar dou to the x, and instead of a second order differential equation, I have here a first order differential equation, which is usually much easier, as is in this case. So I can rearrange it. This way. and I missed a minus here. I'll integrate on both sides. So the ground state is a Gaussian. The only thing I'm missing is the normalization. And to integrate Gaussians, we are already experts, so I'll just copy the result. Putting square root of 1 just to remind that I have here normalization factors, which in this case doesn't matter. What should I do? I just should write it down explicitly, perform the derivative, and I can get more and more terms. In a moment I'll do some general solution, but what do I have here in A digger? Some constant plus first derivative according to x. So whatever I'll get here, I'll have always this exponent, because derivatives and multiplication can't kill the exponent, the Gaussian, times a polynomial. So all solutions of the wave function of a particle in a harmonic oscillator are just a polynomial, that in a moment we'll give it a name, times a Gaussian. Makes a lot of sense. It has to attune far away because the potential won't let it live far away from the center. So that's the role of the exponent. The polynomial will give us the oscillations. We know that a particle in a well has to show the number of oscillation proportional to n, equal actually to n. And that's the role of the polynomial. And we can even say that the polynomial is of order n. First derivative can only create each time one higher power of x. So we know a lot without going into the ugly derivatives here. Okay, instead, so basically I'm finished. I have the eigenvalues, I have the eigenvectors with a simple recipe how to get them. I'm finished. I want to dig a bit more into the eigenvectors. It gives you, in some sense, a different perspective on solution of differential equations. Because, truth be said, I could, instead of doing what I did now, go and brute force solve the second order differential equation and get the solutions. These solutions as most differential equations of second order were solved in the 18th and 19th century by different mathematicians, and these mathematicians gave the solutions their name, and they are known. Probably you ran into them in one of your mathematical courses. And if you haven't taken, it doesn't matter. We solved it. This will just assign a name and properties to these solutions. Okay, so first, because I'm lazy, I don't want to write all the times h bar m omega here. I'll redefine my variable as just to economize on writing, nothing more than that. And I'll rewrite the definitions of A and A dagger using this notation. Y is not an operator. Y is a regular variable. So I'm just rewriting the definition. What we are seeking here is the end solution, which is a function of y, of x, but I'm using this variable change. And just rewrote everything that we know at this point. I want to check what this guy does to this function. Pay attention, it's not psi 0. This is with a minus. This is with a plus. But I can go and perform it explicitly. So the first guy is just y times this, and performing the derivatives gives me 0. Okay. Now I want to perform the same calculation, but for a somewhat more general function. Okay, the same exponent, same Gaussian, but times a general function over y. These two guys cancel. I can go and play this game again and again and again. They'll get so any function times e to the power y square over 2, when I operate n times with this differential form, I get the same Gaussian power of minus 1 to the power of n, just because this minus here multiplies itself, and the nth derivative of the function. Now, but I'm interested in this guy with a minus, not with this guy, where is it? With a plus. But if I use as gy e to the power minus y squared, that that's exactly what I want to calculate. So I don't have to worry all the time about this Gaussian. Can just simply write y to this is a much neater expression than the ones that we wrote previously, because the derivative is only on the Gaussian. Now, we open our math books and discover that this is exactly the definition the Hermite polynomial, which is why is this polynomial? Very clear. The derivative will pull down only powers of y to the n, will leave me e to the minus y squared intact. Multiplying by this guy will give me 1. I'll have only a polynomial here. So, rewriting our solution, and we'll return to our beloved x. Okay, before that I'll just rewrite what's written here. So, sorry on the order here. So, this is the Hermite polynomial times e to the power minus y squared over t, or explicitly psi n and returning to the original definition of x. Okay, this is the solution. Look up the solution of the differential equation that was defined as Hamiltonian in the beginning, and you get this lovely form. Pay attention that actually we almost never need to write this type of equation. Or use this explicit form of the eigenvector. Why? What are we interested usually to pull out of the wave function?
Observable.
Some observable. Okay. I want to calculate the observable for the fourth eigenvector. So I can do here, look up what is a Hermitian polynomial. In a moment I'll explicitly write down formulas how to pull it out a bit more easily from the mathematical knowledge of Hermitian polynomials. Write down an horrible integral, make 7 mistakes on the way, get a wrong answer, and if someone will do it in this way in the exam, if he solves it correctly, I can't say anything, but if he does a mistake, I will tell him it's not a mistake in math, it's because you're, how to say it politely, you decided to hit your head on a wall and you are amazed that you came out with a broken head. Because we can do it much more simpler using the mechanisms that we built. I never write down explicitly the representation in real space. Instead of doing it this way, I write here 4. Okay, we defined it. Instead of x, I'll copy the definition of, I need here to put in the operator x. I don't know to operate on eigenvector 4, but I know what to do if I have a and a dagger. So, for the third or fourth time during this lecture, I'll write down, you have it, but let's write it down once more. A right? So I get okay, so instead of x, I'm writing it in terms of creation and annihilation operator. Have here 4. You have copied it? Give me a moment. This you have already written, so no damage. Okay, so but this guy is simply A is square root of 4, 3. This is 0. This is 0. It's 0. Now, if you're a good physicist, you could tell me it in the beginning. Without doing any calculation, for the simple reason. This potential is symmetric. There's no reason to find the particle with higher probability on the right than on the left. So the average of x must be 0. So that's a great answer. But you have, if you are using it in an exam, be sure that you caught the symmetry correctly. But it's definitely a good answer. If you're a good mathematician and don't know this, you know that this is either an even or an odd function. So an odd times an odd function is even, an even times an even function is again even, and you're multiplying it by x in the integral, so it must be 0. It's x times an even function must be 0. So if you're a good mathematician, again, you'll pull out the results immediately. If you're not sure of either, this, as you have seen, is a very straightforward and easy way to calculate it. The worst is to go and perform the integration, make mistakes, and get something that's not 0. So therefore, I don't recommend, if you can avoid going and performing the integration explicitly, go for it. Not only go for it, I strongly recommend do it. Okay. Just for clarification, what will happen if I'm interested in x squared? Then it's an from the point of view of mathematics, it's an even function times an even function, it's not zero. From the point of view of physics, x squared shouldn't be zero. And going and performing the calculation, all that changed here is squared. Four. Let's write this way. Okay, I can throw out this guy. Why? If I annihilate twice, I'll end up with 2 here. 2 scalar multiplication with 4 will give me 0. This will give me 6, but 6 scalar multiplication with 4 will give me again 0. So I don't have to worry about that. Okay. Yes, but a dagger, we showed that it's n plus 1, right? So 4 times 2 is 8, 9. And good luck to you performing the integration and coming out with the correct prefix. Even if you did, you got that it's not 0. Okay, so basically, in general, I strongly recommend any calculations that you have to perform with a Hermitian oscillator. Use this notation. It's easier, it's transparent, it's quick. Everything is better here. Okay, so that's why I didn't care so much about writing here. Now, you can come and ask what happens if I have a different wave function that is not one of the eigenvectors and I have to calculate something. I'll go into details in the next lecture, But you know that any vector in Hilbert space you can express as a linear combination of the eigenvectors. So change it into a linear combination and life will become easier. At this point, changing it could be a cumbersome calculation because you don't have the initial wave function written in this space. But once you're in this space, life's good. Okay, so I've expressed a few times the point that it's very similar to a photon. But this is not a photon. But what happens is really that you can go and rewrite the Hamiltonian of electromagnetism or other types of waves in nature in a bilinear form. So basically, what you'll get there okay, I'll do a in-between step. What will happen in 2 dimensions here? Let's say we have some kind of harmonic potential in 2 dimensions. Okay. Life behaves the same way in any dimension that we have. Not the results, but the rules of writing down the Hamiltonian and starting the solution. At the moment, I just wrote down a 2-dimensional free particle. Now, without going through the details of the math, you can see that I can do the same fun and games for px squared plus x squared and for py squared plus y squared. And how I'll end up my game? I'll have here 2 parameters because I have 2 independent ends. This would completely straightforward. I separate variables and go through all the steps. I get this result. Now this was a symmetric potential. What happens if I don't have a symmetric potential? Go through the same game. Now, what did they teach you about waves? Basically, they tell you for waves you can separate it into individual modes. That have an energy h bar omega k. That's exactly what the mathematical steps I'm not doing here, but that's exactly what you get if you're taking a classical wave equation, separate it into modes, and then quantize it. So basically, what you'll get is sigma E k h bar omega k n k plus half. Which is the energy of photons. That's what you have learned about the energy of photons. So it comes out for the simple reason I have a bilinear form, can separate it into modes, I can quantize these modes, life's good. Life's good up to disastrous flag that comes up here, red flag. If this is just a constant, who cares? I can add a constant to energy as much as I like. But if k becomes a continuum, this integral diverges. So the quantized energy of any field diverges. And that stops the development. Simplifying, that stops the development of quantum field theory for 20 years. Basically, the greats like Dirac and Heisenberg wrote down this quantization a year or two after single particle quantum mechanics was developed. As you saw, it's almost trivial to develop. Got stuck with the problem that anything that you try to calculate in this language diverges, and had to wait for 20 years till Tomonaga, Schwinger, and Feynman said, don't worry about the infinites, let's rewrite whatever we want to calculate in a form that these terms don't come into the calculation. That's renormalizability. And that's field theory on 1 foot. By the way, what we got here basically is bosons. Why is it bosons? Because you can add more and more packages of energy, meaning more and more photons, meaning more and more particles in the same state, K. For fermions, you'll have to wait to the graduate course how to do it. But always they start field theory with bosons at sea. Okay, so we'll stop here, get some more mathematical knowledge about the Hermish polynomials, and after that we'll move to 3D. We will see that a similar method with some differences will help us very much to solve things that are connected to the angular momentum. Okay, so happy Hanukkah and see you next week.